Problem 102, binary tree level order traversal. So to solve this problem, we need to know two concepts, BFS and binary tree. BFS stands for breadth first search, meaning that we always search the breadth before the depth. So let's say I have a tree that looks something like this, where I connect it like so. Then what BFS says is that we're going to traverse this entire tree in the following manner. We're going to visit this node, then this node, then this node, then this node, then here, then here, then here. The idea is that we go level by level, right? And we expand to include the entire breadth of each depth for each iteration. So that's the idea. For binary tree, a binary tree is simply where every root within the tree has at most two children. It can have one children like this, or it could just be one singular node, but it can never look something like this. That's not binary. So with this, we can continue and solve the example. So basically, we have to return a list where we include a list of lists denoting each list containing the nodes at that given level. So this is level 1, level 2, level 3, which we can see that level 1 has 3, level 2 has 9 and 20, and etc. To do this, we just do BFS. And to do BFS, actually, we need to use a very particular data structure called a queue. A queue has a first in, first out order, just like a queue you would see in real life. Whoever comes to the line first will get serviced first. Therefore, a queue will have a first in, first out algorithm. So the first thing we put in is the first we get out. So we always start by putting the node of the root, which is 3. Then we say, while the queue is not empty, what do? First, we extract the length of the queue. This tells us how many children, or rather how many nodes there are to consider at the given level. Because we're going to be considering children while we add children into the queue. So we need to know this length to know that we're not over extracting nodes from the queue. And we'll see this in practice when we program it up. But the idea is simple. We're going to basically add every single node into the queue as we traverse each level. So for a given node that we pop, we're going to add its children, that's left and right, and append the current popped node into a temporary list that will denote all of the given nodes in that given level, which we append to another variable called res. So with that, we can program it up. And if you think this is daunting, it's not. It's very simple. So as we said, we're going to need a queue, and we're going to get that from a deck. A deck is a queue where you can add items to the left and right directions, but we're just going to consider the left direction in this case. So to solve this, as we said, we're going to first check one condition. If root is none, we're going to return the empty list. Why is this the case? Because we reach example 3, right, where we have nothing to traverse in the tree, so we obviously have nothing to return. So we just return an empty list. And otherwise, that means we have nodes to traverse, and we say res is equal to the list, and queue is equal to the current queue. Now, we always append the root to this queue to consider that the tree is currently still not fully traversed. So while queue is not empty, denoted by while queue, we're going to say what? We're going to initialize a current level list to denote all the nodes at that current level, and we're going to say we're going to get the length of the queue, like so. And for I in range L, that's how many nodes that are at the current level. So we're going to get it, the cur node, by popping it from the queue, by doing pop left. And if cur node dot left is not none, then it has a left child that we need to traverse, and we add that to the queue. The same goes for the right child with the exact same code, except the only difference is that we're going to change left to right, like so. And also, we have to add the current node's value to the current level list. So current level dot append cur node dot val. And after we're done getting all the nodes from the given level, we're going to append it to the result, like so. And with that, we should be able to return the result after we're done traversing the entire tree like so, and it should be good. So let's run it. And we pass everything, so let's submit. And that's the solution.